for one factor, say body mass index, still gives me the need to control for another factor, say age. And table 1's not going to help me that much because table 1 just says among all people, is the age distribution in the intervention group different from the age distribution from the non-intervention group? It doesn't tell me whether those age distributions will be the same or different if we looked at people with common body mass index levels, which we would be controlling for if we built a model that controlled for body mass index. So really what we'd love to know is the distribution of age in the two groups once we are conditioning or controlling for the other risk factors. And that's going to be very hard to do from a display purpose. So table 1 gives us a sense of whether these factors are potential confounders, but doesn't really tell us truly whether they are confounders or not, because it may well be that once we control for age and once we control for sex, that indirectly we're controlling for other factors like blood pressure and cholesterol. Because maybe older people have higher blood pressures. And controlling for age, we're also controlling for their higher blood pressure. But at least it's a starting point. And the bottom line, as the third bullet says here, is we should be liberal. We should be willing to control for all the potential confounding factors. For one, and that means we should be anticipating that at least we might have to include in our model term or terms to represent age and sex, another term for body mass index, other terms for blood pressure, cholesterol. We might have to individually include each separate potential confounder in our model. For one reason, that gives our analysis face validity. If you read a paper and you see in their table that they've controlled for age and sex and body mass index and cholesterol, etc., then you have a sense that they've controlled for all the important risk factors for that outcome. So if you see the factor in your model, you have a sense that you've properly controlled for that confounding factor. So that's one reason to include individual terms for each individual potential confounder. But as the last point says on this slide, that introduces a problem. In this particular data set, I didn't give you many potential confounders. I gave you about 6 or 7 of them, as was listed in that diagram. But the more potential confounders you have to control for in an analysis, put into a model, the more unstable your model is going to be. Because as you add more and more factors into your model, you are making it more difficult for your data set to fit that model. It's similar to the problem of stratification. If you try to stratify simultaneously by many factors, you begin to run out of people in each of your final subgroups. It becomes very difficult to efficiently and precisely measure the effect of the intervention on an outcome if you had to stratify by many factors. And the same thing is true to some sense in a model. So bigger models are more, let's say, prone to problems of efficiency than smaller models. So one of the problems we have is we feel we have to control for all the potential confounding factors. But on the other hand, we're trying to avoid very inefficient models, very large models, very unstable models. And the statistician has to balance those two concerns. So let's say a few other words before we go to SAS about this. So along with that problem of trying to decide what goes into the model, the next problem is how you represent a potential confounder in a model. Now, if you have a continuous confounder like age or body mass index or blood pressure, you have various ways you can represent those potential confounders in your model. You could break people into body mass index classes like we did in the last SAS exercise. One category represents the range of body mass index that people interpret as being in the normal range. Another category represents underweight people. Another category represents overweight people. Another category represents obese individuals. And what we could do is we could include what we call indicator variables, variables that indicate whether you're in a particular category or not. And I'll show you an example of that in a few seconds. What that basically is assuming in the model is that your risk of dying changes when you move from one body mass index category to another. People at normal weight have a different risk of dying than people at overweight. People have a different risk of dying than obese individuals. So it's assuming your risk is different. It changes when you move from one category to another. But it also assumes that people within the same category have the same risk, that all normal weight people have the same risk of dying, all overweight people have the same risk of dying, all obese people have the same risk of dying. So your risk changes when you move out of a category into a new category. We usually refer to that type of a model as a step function. Your risk is increasing or decreasing, like when you climb up a stairs or down a stairs, and the model is assuming your risk stays flat at that level until you step to another level. Another option is to include body mass index as a continuous variable, and we'll do that in a second. And now you have to decide, how are you going to model that continuous relationship? Are you going to include a single term for body mass index, which assumes a linear relationship, or are you going to assume a nonlinear relationship? So for example, if we're talking about a factor like blood pressure, let's talk about that for a minute. We might build a model where we separate our people into 3 blood pressure categories. People with normal blood pressure, people with high blood pressure, let's call those hypertension people. People with very low blood pressure, we'll call those hypotension. We'll make indicator variables that indicate whether you have hypertension or not, or indicate whether you have hypotension or not, and we'll include those indicator variables in the model. So our model will look like what's on the top of this screen. It says your log odds of dying is equal to V0 plus V1 times whether you're hypotensive or not, plus V2 times whether you're hypertensive or not. What that means in the picture is we're assuming that people have 3 different risks. Normal blood pressure people have one risk. Low blood pressure people with hypotension have another risk. High blood pressure people with hypertension have another risk. So in terms of a picture in our minds, this graph describes a step function. The height of each of these lines, or these flat lines, is the risk, or I should say the log odds of dying. And notice the log odds of dying is the lowest for the middle blood pressure range, the people with normal blood pressure, but it's higher for people with hypotension, or it's higher with people with hypertension. This is one way to describe perhaps the relationship between blood pressure and your log odds of dying. Another relationship, and we'll look at this in a second, is we could assume there's a linear relationship. The higher your blood pressure, the higher your risk. The higher your risk, the higher the odds, the higher the odds, the higher the log odds. So this is assuming a straight line or a linear relationship. Your log odds of disease is B0 plus B1 times your blood pressure. Blood pressure measured as a continuous variable, measured in millimeters of mercury. And this graph suggests that there's a straight line linear relationship. As your blood pressure increases by a unit, your log odds of dying increases by a value of B1, the slope of that line. And this might be true in some populations, that higher blood pressure is always worse than lower blood pressure. But another continuous relationship is shown by this last slide. This is also showing a continuous relationship between blood pressure and your log odds of disease, but it's not a straight line relationship. It's what we refer to as a quadratic relationship. It has a hump to it, or a trough to it. It looks like the letter J. It's a J-shaped relationship. And this might be the best way to describe the continuous relationship that blood pressure has to your outcome. Because maybe people with very low blood pressure, hypotension people have high risks. Maybe people with very high blood pressure, hypertension people have very high risks. But in the middle, people with normal blood pressure have lower risk. So maybe this J-shaped relationship, which shows lower blood pressure risk, lower log odds of dying in the normal middle range of blood pressure, but higher risk for the very low people with hypotension, and even more high risk for people with very high blood pressure, might be a better continuous relationship to describe the true relationship between blood pressure and your log odds of dying than the previous slide, the slide that assumed a straight line relationship. So one of the problems we have is trying to decide which is the best way to represent a factor like blood pressure in your model. Should we assume a step function? Should we assume a linear relationship? Or should we assume a quadratic relationship? And basically what you could do is you could fit various models with various assumptions about this relationship and see which model fits our data set better. We'll see that in a few seconds when we look at some SAS analysis. So that's one decision we have to make, whether to represent continuous confounders as categorical or as non-categorical. And if it's non-categorical, do we assume linear relationships or some non-linear relationship? On top of that, we have to make decisions about whether the effect of each of these factors is the same.